Mr. Giroux, in this lesson we're going to be taking a look at rates of change, or motion of a particle or object along a straight line. If s of t is our position function describing an object's position in relation to time, we have the average velocity, which is change in distance over change in time, or delta s over delta t. That, if you want to see it sort of like remembering that average velocity or average rate of change that we talked way about back in pre-calculus, was effectively the slope of a secant line. So we have s of t plus delta t minus s of t over t plus delta t minus t. And when you clean up the denominator, you get something that is really reminding you very strongly of the difference quotient. It just has some different notations because we're talking about particle, linear particle motion over a value of time. So the displacement of an object over the time interval t to t plus delta t is simply the numerator. Again, that is that change in distance. So displacement is change in distance. A little vocabulary there for you. For computational purposes, we'll assume a particle in rectilinear motion, or motion along a line, moves along a coordinate line, which we will call the s-axis. And so here I've drawn an example where our s-axis is vertical, and time is along the horizontal axis. Let's just do a couple of time plots here before we get into some more notes. Position versus time, time curve of a ball thrown straight up. Now, we always talking about objects when thrown without any sort of power behind them generally follow a parabolic curve. Now, I'm not throwing something like a football where I'm throwing it at an angle and I'm trying to hit someone downfield with it or have someone catch it downfield. I'm throwing it straight up. We are talking about rectilinear motion, okay? So let's just say that we put a mark on this y-axis, the position function, and I'm about 6 feet tall, so let's just say that s sub 0 is equal to 6 feet. So the object's not going to start, at position 0 effectively on the ground. It's going to have some initial height. And if I throw it up, it's going to have a positive velocity, but acceleration, which is gravity, is going to be negative. So of course I'm going to throw it up, and then eventually it's going to sort of sit still for a second and then start to fall back down until it hits the earth. So we're going to throw this object, and remember, this is a time plot, so as time passes I'm moving to the right. This is me throwing it straight up, so this path is not the path of the ball per se, it's just time over position relative to the ground. So it's going to rise up, and eventually the gravity is going to bring the velocity of that ball and bring it to 0 and start having a negative velocity as it comes back down to the ground, and that seems like a reasonable sketch of, a ball being thrown up. Initially 6 feet off the ground, it rises somewhat, and then the gravity is going to pull it back down until it has a position of 0, or 0 feet, or inches, or units, whatever the units are, away from the ground. And at that time, we can just stop measuring time. A car that accelerates from a standing start, in other words, a car that is sitting still, going nowhere, its position is not changing. So then you accelerate and then stop the car. So we have a position of 0 until you start to accelerate, and as that car accelerates, its position is going to be starting to change faster and faster and faster with time, and then eventually maybe we have maintained the same constant velocity or speed as you would be looking at your speedometer, you would see, and then it start applying the brakes until the car eventually stops. And then, of course, as time goes on, if the car is stopped, again, its position is not going to be changing. So just a couple of quick examples of plotting or creating a time plot, or a position versus time curve. If your s-axis is vertical, then you're going to consider your movement up as positive. And if your s-axis is horizontal, movement to the right is going to be considered positive. And so again, we have a position function over time here. And I've got an orange secant line, which we do know, again, as I just spoke about in the previous screen, as the average rate of change. And as you let this point defined as the delta, not delta x, but delta t, I wrote it right there, As you allow that delta t to approach 0 and let that second point approach this first fixed point of t, s of t, well then of course we get this, this blue line, which appears to be a tangent line, and the instantaneous velocity is equal to, or v of t, is equal to the limit as delta t approaches 0 of s of t plus delta t minus s of t over delta t. And if you think that looks like the definition of derivative, it is. So basically what we're seeing here is that if I take the position function s of t and take the derivative of it, we have the velocity function. Thus, that's why we're talking about this in our first section covering the basic properties of finding derivatives, because the derivative of the position function is velocity. All right, let's get on to another page of notes, specifically about speed. Now, if we're talking about movement being considered positive, a positive direction, and then we must have a movement that's considered to be a negative direction, right? So, velocity can be negative, 0, or positive. When I throw a ball straight up, its velocity is going to be considered positive as it rises up. But that gravity, and I haven't talked about that yet, but gravity is an acceleration, and that gravity is negative. So the velocity is positive, the gravity is negative. Of course we know it's going to happen. That ball is going to, over time, stop rising, actually at some point have a velocity of 0, and then start to fall and have a velocity again. If we're moving down and that's considered a negative movement, then the velocity is going to be negative. But think about if you have driven a car or ridden in a car, hopefully some form of transportation. They all have speedometers, right? Well, speedometer is basically measuring in some sense your movement over time. Well, there's no negative numbers on your speedometer, right? So speed is the absolute value of velocity. It is not possible for speed to be negative. So speed is increasing, and I gave you a hint of this over here. Speed is increasing when velocity, which is the first derivative of your position function, and acceleration, which I just mentioned it for the first time, gravity is a form of acceleration, well that's s double prime. So if you're given a position function and you find the derivative of that, or the first derivative, then you are talking about the velocity of that object. If you take the derivative again, then that function is going to give you the acceleration. Well, if those are the same sign, if the velocity and the acceleration both have the same sign, then the, then the speed is increasing. But the speed is decreasing when they have different signs, and that's what I was just talking about. We throw a ball up, it has a positive velocity, but acceleration, gravity fighting against it is negative, and that is actually going to slow the speed of the object down. And then as it starts to fall, well, it's going to have a negative velocity. The acceleration of gravity, which we consider negative because it's coming down, has also got the same sign of negative. And so negative velocity, negative acceleration, the speed of that object is going to be accelerating. Or think about your car. If you are going forward with a positive velocity and you put the gas on to push you even faster forward, your speed is going to increase. If you hit the brake, which is going to fight that it's really a negative acceleration fighting that positive velocity, you're going to slow down. So again, speed is increasing when velocity and acceleration are the same sign, and decreasing when they're different. Speed is just simply how fast something is going, and velocity is the speed and, with that sign change being either positive or negative, incorporating the direction of motion together to comprise your velocity. We're going to go over two examples of multiple parts. The first one, similar to this, is going to be a free falling object. And the second example, again with multiple parts, is going to look it's going to be very similar to an actual old AP exam question of a particle in motion, but it'll be horizontal motion as opposed to free falling objects, which apparently the creators of these AP tests prefer because it kind of prevents those students that are very familiar with physics shortcutting the problem and actually having to understand all this calculus I'm trying to teach you. Bang! The position of a free falling object, ignoring air resistance, is described by S of t is equal to 1/2 g, which is going to be our gravity, times t squared plus v sub 0 times t, or our initial velocity times time, plus s sub 0, which is going to be our initial height. And at this point, we actually have to be given this formula. When we learn how to do integration, we'll be able to actually figure this out on our own. Our example is, at time is equal to 0, an object is thrown from 64 feet above the ground, and it's been thrown upward with an initial velocity of 48 feet per second. And again, that initial velocity is positive because we threw it upward, and that is considered a positive motion. Remember that gravity acceleration is negative 32 feet per second, or if you're working in meters, we're going to work in feet, but in meters that's going to be negative 9.8 meters per second. So our position function then is going to be s of t is equal to 1/2 negative 32t squared times, I just said that, times t squared plus 48t plus 64. And cleaning that up, we get s of t is equal to negative 16t plus 48t plus 64. And the first two parts of this, actually many-part example, is going to be really not a calculus question, but an algebra 2 question. When will the object hit the ground? And then, what is the average velocity of the object between 0 and 1.25 seconds? Now, really, neither one of these questions are calculus questions. They're algebra 2, and maybe you might have had average velocity in algebra 2, or certainly pre-calculus. Now, you know we're high-tech here with my high-end boards here, so let's get our window and picture here. Yes, perfect. Voila. Just so I have something to look at. We have this power of 2, so it is a downward opening parabola. And yeah, okay, and it's going to reach its maximum height. We're going to find that actually in part of the work we do at 1.5 seconds. And I can see now that I got this out of the window, it's a little bright. Okay, that's a little better. So with our chalkboard here showing us our downward opening parabola, which is our position function over, or position graph over time, we're going to find, let's see here, well, if it hits the ground, then the position of the object is going to be 0, right? So we have 0 is equal to negative 16t squared plus 48t plus 64. And just to speed this up a little bit, I'm going to reveal this in small steps. You have to watch me write, but we're going to factor out the negative 16 and then continue factoring to solve this quadratic for 0. So as promised, we factored out the negative 16. We got t squared minus 3t minus 4, and factors of negative 4 that add to negative 3 are negative 4 and positive 1. Setting each one of these factors equal to 0, we find that this parabola is crossing the t-axis at values of negative 1 and 4. But we're talking about time, of course, and there's no such thing as a negative time. Can't go back in time and change things, right? So the object is going to hit the ground after 4 seconds. What is the average velocity of the object between 0 and 1.25 seconds? Well, we're going to find that in a minute. I'm kind of giving the answer away, but the maximum height of the object is going to be reached after 1.5 seconds. So the average velocity from 0 to 1.25 is going to be, again, the slope of a secant line, and since the object is rising that entire time, our average rate of change, or our average velocity, is going to be positive. And again, that is just basically finding slope, right? Slope of a secant line. So let's get that work up here. So here we have s sub t plus delta t, if you will, so negative 16 times 1.25 squared plus 48 times 1.25 plus 64 minus s sub t, which is negative 16 minus times 0 squared plus 48 times 0 plus 64 over 1.25, excuse me, minus 0. That gives us an average velocity of 28 feet per second, or a speed of 28 feet per second. So it looks like I'm saying the same thing, but if I'm talking about speed, remember it can't be negative, so I'd have to add a little extra phrase here that the particle or the object is moving up. Now, again, we had what? We had an initial velocity, I forgot what I wrote here, an initial velocity of 48 feet per second, and now the speed has decreased and actually velocity has as well, but focusing on speed here, the speed has decreased to 28 feet per second. Why has the speed decreased? Well, because the velocity was positive, thrown up 48 feet per second, and the acceleration of gravity is negative, thus the speed is slowing down. Alright, let's get this all out of the way, and I got a lot more parts to this example. Again, what is the average velocity of the object between 2 and 3 seconds? Well, that's the same as the previous question, so let's get a look at that answer. I just wanted to show you a second example or second part using the same average velocity formula, just to point out again that in this case, because we're at a time point finding an average velocity between 2 and 3 seconds, and then that object at this point is got a downward movement or a negative movement, then our velocity comes out to be negative. But if you're going to say speed, remember speed is the absolute value of velocity. So the speed of the object would be described as, again, 32 feet per second, drop the negative, and then to indicate the direction you need to say, well, it's moving down. So we have an average velocity of negative 32 feet per second, or in speed of 32 feet per second, moving down. Now, what is the object's velocity at 2 seconds? Well, the difference here at part D is I didn't say the word average velocity. So we're moving from now basically pre-calculus into calculus, and I want to find the instantaneous rate of change, or velocity, instant velocity. Well, that means that we need, like I discussed earlier, the derivative. And if s of t is equal to negative 16t squared plus 48t plus 64, then s prime of t, let's put it down here, is going to be using the power rule. Bring this exponent down, so negative 16 times 2 is negative 32. Reduce that power by 1, which is going to be negative 32t to the first power. Almost looks like I'm making a derivative mark here, but that's the first power, and actually I don't need to write that, correct? Plus 48t, bringing that power of 1 down. 1 times 48 is 48. And then, of course, the t has a power of 0, so it's just going to be plus 48. And the derivative of a constant is equal to 0. So if s of t is this function here, then s prime of t, or the derivative of s of t, is equal to negative 32t plus 48. And, of course, if this is the position function, which it is, the first derivative is equal to the velocity. So this becomes, or is, our velocity function. And if I want to find the velocity at 2 seconds, all I have to do is plug 2 into this. And so we have v of 2 is equal to negative 32 times, let's clean that up, negative 32 times 2 plus 48 is negative 64 plus 48, and that is going to be equal to, let's see here, 64, 24, 24 minus 8 is going to be negative 16 feet per second, or again, the speed, the instantaneous speed, or the instantaneous rate of change, actually, let's just say speed, right? Speed is the absolute value of velocity. It would be 16 feet per second moving, again, down. Okay, let's get on to our, I feel like I've made a mistake here. Yes, well, I didn't really make a mistake, but in my notes I had this copied at, oh, never mind. I need to stop looking at my notes and just start thinking. Next part of the examples, here's what I glanced at in my notes. I was doing velocity and I all of a sudden in my notes saw 3 and I thought I miscopied something. Well, I want us to now find the instantaneous velocity at 3 seconds, just simply because I want to emphasize that we have passed that 1.5, which we're going to talk about in the last part, and the slope of the tangent line is going to decrease as, well, basically we can see the slope of this downward opening parabola is decreasing as we get closer and closer to the value of 4. So we should be finding that our instantaneous velocity at 3 seconds is going to be more negative, if you will, or the absolute value, right, the absolute value velocity speed, the speed should be increasing because now we have a negative velocity and the acceleration is also negative. So let's reveal that answer. Probably already know it. So indeed, we found that our velocity is negative 48 feet per second, or the speed is absolute value of that 48 feet per second moving downward. And the speed increased because the velocity and the acceleration are both negative, and we're going down at a faster rate. Okay, so then when is the object going to reach its maximum height? Well, because our function, our position function, is a parabola, there's two ways we can deal with this. We can just go back to finding the x of a vertex, which is found by doing x is equal to negative b over 2a, and that is going to be negative 48 over 2 times our a value, which is equal to negative 16. That comes out to be 48 over 32, which is equal to 1.5 seconds. Now there's a more calculus way to do this, which is kind of a preview of a topic we're going to study later called the first derivative test for finding relative maxima and minima. And that is going to be to remember that our position function was s of t is equal to negative 16t squared plus 48t plus 64. And our first derivative is negative 32t plus 48. So our first derivative is, in this case, because we're talking about a position function, now we're talking about velocity. So it's going to reach its maximum height when the velocity becomes equal to 0. So I can set this first derivative equal to 0 and get negative 32t plus 48 is equal to 0, and again that comes out to be t is equal to 1.5 seconds. Alright, well I can't just say because the velocity is equal to 0 that we have reached the maximum height, other than just putting it in context of this problem. But maybe if this function isn't just a free-falling function, there's no reason why an object can't come out and have a velocity of 0 and then start to rise again. So really, and we'll be talking more about this again later in a chapter within this, or section within this chapter called the first derivative test. Just because you have a slope of 0 doesn't necessarily mean that you're going to have a relative max or min, because the graph could just be taking a break and then in this case start to rise again. Well, we're talking about a free-falling object, so we know that's not going to happen, but to give you a preview of this first derivative test, yes, at t equals 1.5, my first derivative is equal to 0, or the velocity is equal to 0. But what's even more important is that our first derivative is less than 0 when t is less than 1.5, and our, not less than 0, I'm talking about greater than 0, right? Our velocity, or our first derivative, is positive up until we get to that 1.5, which is when the first derivative is equal to 0, or the velocity is equal to 0, and then the first derivative is less than 0 when t is greater than 1.5. So the slope of the function goes from being positive to being negative on the left and the right hand side of that point where the first derivative is equal to 0, or the velocity is equal to 0. So I could also say in terms of this problem, positive velocity, velocity of 0, and then importantly a negative velocity, that sign change of the first derivative going from positive to negative at that point of 1.5, or at that t-value of 1.5, shows that that is a relative maximum, or the highest that this object, the highest this object will achieve before it starts to fall again. Next example. Last example. A particle moves along a straight line. For t between 0 and 4 inclusive, the velocity of the particle is given by v of t is equal to negative 2 plus 2 times t to the t squared plus 4t raised to the 4/5 power minus t cubed. And the position of the particle is given by s of t. We haven't talked about integration yet, and actually that was a little bit part of this old AP exam question, so we're going to be amazingly focusing on velocity. And really the key thing to remember or focus on for this problem here, find all values of t in the interval where t is between 1 and 3, not inclusive, for which the speed of the particle is equal to 3. Well, we have to remember that the speed is equal to the absolute value of velocity. So, if you were to just take this velocity equation, set it equal to 3 and solve, you're going to lose a lot of points because you haven't recognized that the speed is the absolute value of velocity, so you actually have two equations to solve for. We have that this can be equal to 3, so 3 is equal to negative 2 plus 2 times t squared plus 4t to the 4/5 power minus t cubed, and you have to solve for this being equal to negative 3, because if the velocity is negative 3, the absolute value of negative 3 is 3, and we are looking for where the speed is equal to 3. So we have negative 2 plus 2 times t squared plus 4t to the 4/5 power minus t cubed. Let's get these equations set equal to 0 and look at how we need to solve these with our calculator and write the answers up here on the chalkboard. Here we are with our TI Nspire. Mine happens to be a CAS version. We're going to open up a new document. We're going to add graphs, and we're going to type in the equation. Now, if you set the velocity equal to 3 and set it equal to, and then subtract both sides by 3, you get 0 is equal to negative 5 plus 2 parentheses, excuse me, let's try that again, times parentheses. Now it is in terms of t, but you know, when I'm graphing this, it's got the independent variable of x. So I'm going to do x squared plus 4x, close the parentheses up, hit an exponent. I want to do a fraction, so I'm going to come over here in second division, 4 over 5. Put this arrow over minus t, or x, to the third power. And we're going to hit graph. And we were looking for all values of t in the interval from 1 to 3, which the speed of the particle is equal to 3. So I'm looking for x-intercepts, but I only care about the ones that are between the values of 1 and 3. So I'm going to hit Menu, go to Window and Zoom, Window Settings, and I want that x-min to be 1 and max to be 3. Hit Enter again. We're OK. And now I want to find that x-intercept right there, the solution to our equation. So I'm going to hit Menu, and we're going to analyze the graph, find a 0. It's asking for the lower bound, so and now you'd be touching using the touchpad here. Put that to the left, click the center, go to the right, and click the center again of your touchpad. Now, for some reason on my computer software here, I cannot get the calculator on the graphical solution process to go to 3 decimal places, even though when I went to Menu and Settings, let's see here, let's try float 4. Oh, there we go. Just before I started the video, couldn't get that to come up. So you can change the setting on your graphing page to get that decimal to go out to 3 decimal places, like they're expecting us to do, like say on the AP Calculus exam. And of course, if you have a CAS, you can add a page, and maybe you would have solved it this way in the first place. Add a calculator, and you can go to Menu, Algebra, Solve, and we're going to type that equation in again. We're going to do negative 5, I should have done copy and paste to do this instead, plus 2 times parentheses, well, I can go ahead and use t now, t squared plus 4t, close the parentheses up, exponent, second division for fraction, 4/5, arrow over, get out of the exponent form there, minus t to the third. And we want that to be equal to 0, so, or at least we're, whoops, excuse me, we're wanting to solve this for equaling 0, so now equals 0, comma, when we want to solve for, of course, our variable t. and hit enter. And you can see there's more than one solution, but if I arrow over now, I can hopefully, there we go, get into the answer there. And arrow over and we find that 2.2752 da 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 da, but we only need to go to 3 decimal places, and that is our solution to our equation when the velocity is equal to 3. Now when the velocity was equal to -3, or well actually, you know, because we're looking for when the speed is equal to 3, but that's the absolute value of velocity. So when we let the velocity equal -3, we can set that again equal to 0. Now I'm going to come up here, so I have to type that in again, and hit enter, and then arrow over here and change that -5, because when I have the velocity equal to -3 and I add it to both sides, this is going to be equal to not -5, but 1. And hit enter. And as you saw on my you will see on my blackboard, that solution there is 2.811. Or of course we can do that graphically. We can hit tab, arrow up, arrow over to change that -5 to a +1. Hit enter. And let's see here. Let's grab this page. I'm going to, again, you would push down on this tab, this touchpad in the center to hold the graph. Or do I need to do that? Let's see here. There we go. And menu, analyze graph, 0, lower bound, upper bound, and there's the same solution you can solve graphically if you don't have a CAS calculator of 2.811. Alright, so we have our approximate times of 2.275 and 2.811. Always round these off to the third decimal place, or the thousandths place. Okay, so finding all time, or find all times t in the interval from 0 to 4 at which the particle changes direction. Okay, so I'm going to the right, my velocity is positive, stop and change direction and go backwards, my velocity becomes negative. So we're going to find where the velocity is equal to 0, and that's going to be 0 is equal to -2 plus 2 times t squared plus 4t to the 4/5 power minus t cubed, and we'll solve this for 0, just of course like we did here, and that is going to come out to be times of 0.238 and 2.588. Well, it's not enough just to say that that's when the velocity is equal to 0. To justify our answer, again, our velocity, if I'm going to change directions, if my velocity is positive, becomes 0, and then becomes positive again, I didn't change direction, I'm still walking to your right. The velocity has to change sign. So we need to set up some intervals based on going from 0 to 0.238, and then from 0.238 to 2.588, and then carrying on to the final time value of 4, and show and state that the sign of the velocity function is changing. That's when the object changes directions. Let me pause that and get this up here. Try again. And I'm running out of room, but if I were taking an AP exam, I would now, with my intervals and the signs of my velocity within these intervals shown in full sentences, I would say that the object, or the particle changes direction at time of 0.238 seconds because the velocity changes from negative to positive, and then it also changes direction at time period of 2.588 seconds because the velocity changes from being positive to negative. So it does change direction twice. I got one more example and we're going to be done finally. Is the speed of the particle increasing or decreasing at t equals 3? Okay, unlike the previous example where I gave us the position function and then we found the first derivative, which was velocity, and then we talked about the second derivative being acceleration, but the acceleration of gravity was already negative. Here we have to remember that we were given the velocity function right off the beginning. So is the speed of the particle increasing or decreasing? Well, speed increases when velocity and acceleration have the same sign. and I don't want to find the derivative to find the sign of velocity again. That's what I was given. I was not given the position function. So v of 3 is equal to, right at the top of my head, when I plug 3 into this velocity function, I get approximately, not equal to, but approximately negative 6.154. And I don't really care about what the velocity is. If the question is the particle increasing or decreasing in speed, I just want to see the sign, and it's negative. Now, the derivative of the velocity is equal to what? Acceleration. We have a position function. With the derivative of the position function, the first derivative is velocity, and the second derivative is acceleration when we're starting from the position function. Well, we start with the velocity function, so the first derivative is acceleration. So that's what this is. And again, if this is a calculator question, we're not expecting you to find the derivative of this function by hand. You can find the derivative at a point with your calculator, and v prime of 3 is equal to negative 18.297. So, since, and you might want to write this as a summary statement, and actually maybe I will too, just to pause it so you have to watch me write. The speed is increasing because the signs of velocity and acceleration are both the same, in this case, negative. So, I'm Mr. True. Thank you for watching. I'm going to show you how to find that derivative, the value of the derivative at 3 if you don't already know how to do that with your calculator, or at least with an TI Nspire. So, except for that, I'm Mr. True. Go do your homework. Okay, so we have our original velocity function in here, graphed already, negative 2 plus 2 times such and such, you can see. If you want to find the derivative of at a point on a graph, even if it's not a CAS calculator, you can get the function up there on the screen. You can hit Menu, Analyze Graph, look for dy dx, and that same menu is in any Texas Instrument calculator, even if you have an 83 or 84. It'll ask you for the position. Now, 83s and 84s won't ask you for that. You can just type in the number, though. We wanted to find the derivative at x equals 3. So just type in, hit 3, hit Enter, and there is our f prime of 3. Of course, the derivative of velocity is acceleration, so our acceleration at 3, at t equals 3, is negative 18.3. Now, I had negative 18.297 on the chalkboard, so you can go ahead and enter or put in a calculator page, or you can just, of course, hit your toggle button to get to the calculator page of your scratch pad. Hit Menu, go to Calculus, find derivative at a point, and with this menu option, it's saying here, okay, variable in terms of x, I want to find the derivative at 3, so I'm going to type in the value of 3, hit OK, and I have copied that function or that equation already into the calculator, so now I can do Control V so I don't have to type it for you guys right and make this video any longer. There's the velocity function, and we're going to find the derivative of that, which would be the acceleration at time equals 3. And, well, got an exact value answer, so we can hit Control Enter to get the approximate answer. And there's the negative 18.297. Again, thank you very much for watching, and please subscribe, like, and rate if you like the video.